the left bottom figure shows the whole atmospheric CO2 concentration of the whole atmosphere, which has been captured and retrieved by the greenhouse gas observing satellite of Japan from 2009 to 2018. And in 2015, the average CO2 carbon dioxide in the atmosphere reached 400 ppm. And after that, it showed an increasing trend of the past few decades. And the middle bottom of this presentation shows three spatial variations of carbon dioxide worldwide in 2009, 2012, and 2015, and the concentration showed an increasing tendency. We know that fire and biomass burning, especially in Southeast Asia, Amazon, and Africa, are the unique disturbance on ecosystem processes and dynamics because it can cause a loss of carbon that has been stored in large terrestrial pool. For example, the live vegetation, the dead vegetation, the organic carbon, and the litter, so which have a large impact on the ecosystem productivity, as the presentation yesterday by the Muraoka sensei from Japan. And at the same time, it also releases a huge numbers of greenhouse gases and aerosols into the atmosphere, which have a large impact on the climate system. For example, the greenhouse gases usually has a radiative forcing component of positive, and the aerosol also usually shows the negative forcing radiative forcing. Meantime, the fire presents obvious characteristic of spatial and temporal variation, especially for small-sized fires in Africa. Here is an example derived from NASA MODIS instruments, which monitors the small fire occurrences over the past few decades, of the past few seasons and months, and which shows that strong spatial variation in different periods and different months. So the global fire emission database, we call it version 3, estimated the monthly biomass burning emissions since 1997 until now, with a spatial resolution of 0.5 degree and a monthly time step. And it can calculate the biomass burning emission of trace gases, greenhouse gases, aerosols, and pollutants, air pollutants worldwide, but it has a coarse spatial resolution with 0.5 degree. And the red figure shows the Southeast Asian phenomena, which usually have very small fire emissions. The red figure is the fire size in Southeast Asia, which shows that the size is relatively small. And due to the slash and burn plantation and land clearing process in Myanmar, Laos, Cambodia, and Thailand, especially the mainland of Southeast Asia, and also the peatland conversion for palm oil plantation, especially in Sumatra and Kalimantan of Indonesia. The fire size in this area are relatively small. Here are the fire types in Southeast Asia and their effects on air quality in Singapore. The main fire type in Southeast Asia is the forest fire, shrubland fire, crop residue burning, peatland fire. And during the ENSO event induced fire episode, they released aerosol, which has a very bad impact on the neighboring countries, especially the Singapore. You can see the air quality deterioration, especially during the fire days. So just now we mentioned the GFED3. GFED3 has a spatial resolution of 0.5 degree. So the coarse grid data usually has difficulty in explaining very small fire characters, especially due to the heterogeneity and variability of the land surface process. And these two pictures are from the MODIS active fire product, MYD and MOD14 product, which shows the fire counts. We can see in Kalimantan, there are many fire counts. However, the fire spots are very small. So the coarse grid data cannot explain the small fire character. Therefore, in our study, we want to investigate the spatial and temporal patterns of the small fire carbon emission with higher spatial resolution, just for more clear understanding of the contribution of fire to the regional and global carbon cycle and its effects on global warming. And here we used a physical-based model. We call it the BEAMS, Biosphere Model Integrating Eco-Psychological and Mechanistic Approach using Satellite, which has been developed by the Sasai in Japan. And I use this model to improve it and embed with fire carbon process. This model can simulate or estimate the carbon process, ecological process, hydrological process. For carbon process, the photosynthesis, the respiration, the biomass generation, and the soil organic matter will be simulated. In energy process, the downward long wave, short wave radiation, the sensible heat, the latent heat, and the ground heat, and the solar radiation will be estimated. For hydrological process, this model can simulate the evaporation, transpiration, two process. Of course, the canopy storage, the percolation, the soil water allocation, and interception. All this process can be simulated. For fire carbon emission process, when fire happens in a vegetation, its biomass, including leaf, stem, root, litter fall, soil organic matter will be consumed from carbon stock into carbon fluxes. Therefore, we use we added the fire carbon emission process in this equation. And the dynamic of biomass the change of biomass can be expressed as the minus of GBP, RA, litter fall, and carbon emission process. And usually the fire-induced carbon emission process can be calculated as the product of burned area, fuel loads, combustion factor, and emission factor. There are four important input parameters in this study. Therefore, we deal with all these input parameters by using different models or different satellite or observation data. For burned area, we collected the MCD64A1 burned area products, which derived from models. For fuel load in this study, we used our improved model to simulate the biomass, including surface litter and organic matter. And combustion set factor is defined as the fraction of available fuels that has been exposed to fire and that are usually actually burned. In fact, not all the fuels can be burned because of its volume and area ratio. So usually, parts of the biomass can be burned during fire. So how many percent can be burned? They were determined by the water content. Here we use the soil water content and the moisture condition to linearly scale the combustion factor into each pixels. Emission factor actually was derived from the reference of the other published study, which defined as the emitted trace gases or aerosols per kilometer dry matter burned during fires. Here's the MCD64A1 burned area product derived from models from 2001 to 2010 with spatial resolution of 5 kilometers. And we can see the spatial distribution shows that Southeast Asia has significant extensive burned areas, especially in northern part, that is the mainland of Southeast Asia, especially the western Myanmar, North Thailand, North Laos, and East Cambodia. While in the equatorial ESEA region, more burned areas were captured in Indonesia, Sumatra, and Kalimantan, especially South Kalimantan area, because of the peatland burning. After we collected all the required input data for the model simulation, including elevation, precipitation, solar radiation, temperature, LAI, FPA, albedo, wind speed, relative humidity, land cover type, soil moisture, soil texture, soil depth, And we ran this model for 10 years with monthly time step. And before that, we should first spin up this model to make it more agreed with the observation side. And the left figure is our simulation results. Total biomass here means the above ground and below ground biomass. And we can see that the high biomass density can be found in the equatorial Asia. And in Southeast Asia, especially in forest cover area, it also records a very high value. And right figure shows the comparison of our simulation with other studies, which has been published in PNAS. And this study used the observation site and satellite retrieved site point scale data sets, and we found our study agreed well with it, although some little bit under overestimation, especially in cropland and forest land. And this figure, this is the result of our estimated annual fair carbon emission from biomass burning with 5 kilometers degree, 5 kilometers spatial resolution. And we found that in northern part, in the western Myanmar, and the North Thailand, the North Laos, and East Cambodia experienced unprecedented strong spatial variation and high amount of carbon emission, fire carbon emission. While in the equatorial region, the South Sumatra, South Kalimantan, and parts of South Papua New Guinea also witnessed high emission. Compared with the GFED3, which has 0.5 degree, we found that our study shows priority and advantages in detecting more small fires emissions. Since the two parts in Southeast Asia have different driving factors, especially the fire carbon emission process. Therefore, we divide the whole study area into the two parts. In north part, we found that the slash and burn cultivation is the main driver. And in equatorial Asia, peatland burning during August, September, and October is the main factor that caused the fire emissions. And the background is the gray background value color shows the ENSO index, which means the higher, the darker, and the ENSO index become larger. So we can see in equatorial region, the red figure shows that in ENSO event, and the fire carbon emissions reach a very high level, reach a very high amount in 2002, 2004, 2006, and 2009. And during these 4 years, the ENSO events shows very high. And the ENSO event induced carbon reached a very high level. This was because by the periodical drought in this region. Another method to quantify the biomass burning emission, we use the inventory method. Well, inventory methods are very generally based on the bottom-up method, which you should include the biomass density, burn area, and emission factor and combustion factor. And usually the biomass density are quantified or defined based on the land cover type of administration level. Here we use the vegetation index to quantify the biomass density. Another improvement is the combustion factor. Well, in previous study or the early study used the land cover type to quantify the combustion factor for each pixel. And the general, the simplification usually overlook the differences and spatial variations. Therefore, we use the vegetation cover index to represent the combustion factor in this study, which is a large improvement. Let's look at the results. And this time we quantify the annual CO2 emission from biomass burning with 1 kilometer spatial resolution. After comparing with the GFED3, we found large emissions were detected in Cambodia, Myanmar, Thailand, Indonesia. And high resolution data can capture actually small fire emissions, which were frequently misinterpreted in coarse-grained data sets. After quantification of the average annual emission for each land in Southeast Asia, we found that forest fire is the dominant contributor to the total amount of biomass burning emission. And peatland emitted the largest emission after forest. And crop residue burning in this study only integrated 4 kinds. Therefore, it shows a little bit underestimation comparing with other studies. We use the 2 different methods to quantify fire CO2 emission. The final results are listed here. The model beams-based CO2 emission can reach up to 800 TG, while the emission inventory of the CO2 emission can reach up to 761 TG, while GFAT3 shows the result of 685. Although our 2 methods are higher than it, but it showed good agreement with GFAT3. The overestimation was due to the small fire carbon emission process. So our results are reliable. Currently, there are many data sets on biomass burning emission globally can be available. For example, GFED3, GFED4, GFAS, and FINN, and also GG, which is developed by our team. So we are usually questioned by which biomass burning emission inventory are more suitable, are more appropriate, are more reliable for this atmospheric transport simulation as input data. So we divided the whole study global area into 16 fire types, from the boreal North America and temperate North American, Central American, Mexico, Northern Hemisphere of South America, South Hemisphere, South America, Europe, Middle East, Northern Hemisphere, Africa, and Southern Hemisphere, Africa, Boreal Asia, Central Asia, Southeast Asia, Equatorial Asia, Australia, and Oceania, by using the major fire types in this area. And then we introduced the coefficient of determination factor or indicator to indicate the similarities and differences among these 5 inventories. We finally found that the GFAT3 and GFAT4 show the best correlations between each other. And for overestimation area, the FINN data sets in Southeast Asia has very high estimation compared with other study because of the savanna and cropland burning. Well, in Southern Africa and the savanna and the Amazon forest fire burning due to the underestimation also presented differences. So in our further study, if we want to use the simulation if we want to use the data sets as input for atmospheric transport simulation, please be careful of the FINN data sets, although it has a very higher spatial resolution with 1 kilometer degree, with 1 kilometer. And then we compare the 5 data sets from month to month and from year to year, from January to December, and from 2002 to 2011. Our results showed good agreement with the above conclusion. We know the biomass burning is the main source of aerosol at global scale worldwide, but its contribution varies from country to country, from pixel to pixel. And then we collected the GFAT3 CO2 fire emission data sets and its corresponding AOD, aerosol optical depths, also from MODIS, and make correlation coefficient of the 2 data sets. And below it shows the correlation coefficient. We found that in Amazon, in southern part of Africa, in Southeast Asia, and also some parts of Siberia and Australia, the correlation showed good agreement, which can tell us that in this area, the The biomass burning is the major source of the regional aerosol. However, in other parts, for example, in China, most of China and in India, their correlation the correlation are very low, because in this area, the aerosol come from the human emissions, especially for the industry process. For high resolution emission, actually in tropical area, uh, including including 76 countries, are all developing countries, which rely not only on biomass burning, but also human waste and field work for daily heating and cooking. Therefore, we targeted our study area into the tropical continents. Not only forest fire emission, but also open residential waste, damp waste, and fuel wood combustion are also very common in this region. Therefore, its emission of greenhouse gases can also reach a very high level. And this is our estimated total burned biomass, including the three parts: vegetation, waste, and fuel wood. Here is the biomass burning emission. Let's take carbon monoxide as example. For vegetation burning, actually the vegetation burning in Central Africa and the southern part of Africa has reached a very high amount. While for waste burning and fuel burning, which depends on the human density, of course, in India, the values reach a very high amount. The total amount actually can reach up to 400 million gram carbon monoxide per square kilometers. So this is very high values. And not only the CO, but also carbon dioxide and other methane greenhouse gases were also quantified. And then we compared our study with the EDGA data sets. We showed the data sets showed that our study showed good agreement with EDGA, although overestimation for most of gases, because our study has 1 kilometer degree. Therefore, it has advantages in detecting more small-sized fires. And the bottom figure shows the vegetation burning emission in the three continents between this study and the GFED3. Of course, it also showed good agreement, although some overestimation in PM2.5 and organic carbon. After comparing with the GFED3 and GFED4 with 0.5 degree and 0.25 degree, our study with 1 kilometer resolution has advantages in detecting more small-sized fires. And below are two pictures of carbon monoxide and a black carbon for each land tab in each continent. In in Asia, the major biomass burning emission are the field burning, especially in India. While in America, in Africa, the dominant factor is the open vegetation, especially the forest fire and the savanna burning in these two regions. And mercury, we can see mercury emission from biomass burning also are very common. Mercury is a global pollutant after carbon dioxide. And biomass burning actually is the primary source. Climate change over the past few decades increased the intensity, frequency, size, and the duration of fire occurrences over the past 20 years. And red figure is the annual percentage burned area by fire. Actually, in most of China, it showed decreasing trend, while in Southeast Asia and Amazon and Africa, it also experienced an increasing tendency. And the bottom figure is the global mercury cycle. So biomass burning of the left part actually increased the emission from wildfire. Actually, plays a very important role. And the long-term trends are required for source apportionment, transportation simulation, and environmental assessment. Therefore, we use the bottom-up method to quantify the biomass burning emission in the equatorial region. So we improved the four parts. For burn area, we use the burn area product MCD64A1. And in this study, we included the active fire product MOD14. And for field loads, we use the satellite and observation data of biomass density to replace the traditional method of land cover-based or administration boundary-based field load tags. For combustion factor, here we classify the vegetation into three kinds: forest, woodland, and grassland, based on the tree cover fraction from modest vegetation continuous field MOD44B product. And we classify them into three kinds. And for each kind, we have a different equation to quantify it with pixel by pixel. Here's the monthly MCD64A1 burn area percent of the whole study area. We can see that in Central Africa and the southern part of Africa, due to the drought event, and the fire actually persists all year round, around maybe 8 months or 9 months per year. So the burn area percentage is relatively very high. Well, in Southeast Asia, actually the percentage are relatively small. Here's the simulated above ground biomass. We found that in Southeast Asia, the biomass density actually were very high. Here's the quantified combustion factor. So the field tabs were classified into three kinds, and we make the CF, quantify the CF according to each equation. Here's the emission factor, which was derived from the published and study, which are compiled by worldwide data. We classify them into 5 tabs: forest, woodland, grassland, shrubland, and peatland. After collecting all the required input data, we ran this model from 2001 to 2017 and calculate the mercury emissions in the tropical continents. Here's the spatial distribution of biomass burning mercury emissions. We can find that although Southeast Asia has a relatively low percentage of burned area, but its amount actually are very high, especially in Western Myanmar, North Thailand, North Laos, and East Cambodia. Here's the temporal variation of mercury emissions from 21 to 2017. This is the interannual variation for the 5 land tab. We found that 2004, 7, 10, and 15 are experienced as the peak value. After checking the burn area product, we found that because the forest fire in these 4 years reached a very high value, therefore resulting in the high emissions of mercury emissions. For interannual variation, that is the monthly variation, there are 2 peaks every year: March, August to September. For August, this was because the forest fire, while for August and September, this was due to the forest fire and woody savanna burning. Actually, all study area, crop residue accounts for a very relatively small percentage. Here's the annual mercury emissions for each continent. Here we can see that 3 continents out of Asia accounts for a small area, but its amount can be comparable with other 2 continents. So the total amount are very high. However, the 3 continents are relatively stable. Here's the comparison of our study with published study. We found that our study are comparable and reach reached a good agreement with the published studies. And these two bars shows that the dominant factor of each biomass burning emission in three continents, in, in America, South America, and in Asia, the dominant contributor are forests. That means the forest fire was the predominant factors, drivers of the regional mercury emissions. Well, for Africa, this phenomenon changed into woody savanna and shrubland burning, since the major fire type are woodland savanna burning all year around. After comparing with the burned area of our study, we found that actually burned area is the determining factor which can control the spatial distribution and variations of the mercury emission. Well, however, how much the amount of mercury emission can emit into the atmosphere actually depends on the burned biomass. Of course, our study has very large uncertainty because of the input data all have large uncertainties. And finally, we ran the Monte Carlo model to distribute and allocate the uncertainty into each kinds of trace gases. Here's the biomass burning emission of the total amount for all the trace gases, including the aerosols, pollutants, and greenhouse gases for forest, woody savanna, savanna grassland, cropland, peatland in Americans, Africa, and Asia, and their total amounts. And the left figure shows that our study are agreed with the other published studies. And this result has been published the last year in Journal of Clean Air Production. Except the mercury, the carbon dioxide also present the similar the patterns and distributions with mercury emission. That it means that all the amounts are released from the fire process. Here we use another indicator defined as the ratio of carbon dioxide and burned area. We call it the biomass burning emission intensity, and to express which area shows much more intensity. And we can find that Southeast Asia witnessed more emission for each unit of burned area, so which can indicate that more burned biomass when fire occurs. So the fire in Southeast Asia can release more emissions. And if you want to control the air pollution or the air greenhouse gases emission, so the fire control is a prerequisite. We know that the MODIS data set has 500 meter spatial resolution, while for small agriculture fire sites, especially less than 500 meters, and the short time period of fire. For example, Terra and Aqua overpasses at local time of 10:30 and 13:30. So the small fire cannot be detected or captured successfully. So in this part, we use another method. We call it the fire radiative energy, and to derive the burned amount from the energy perspective. For forest, shrubland, savanna, grassland, and peatland, we use the MCD64A1 burn area product. While for agriculture small fire, we use the MOD14 product to quantify the biomass burning emissions. We selected our study area in Northeast China since it includes all 5 major fire types: cropland, forest, grassland, shrubland, and peatland. And after collecting all the required input data sets, we ran this model. The emission inventory, including PM2.5, PM10, black carbon, methane, carbon monoxide, carbon dioxide, and NH3, and MVOC, NOx, OC, and SO2. This in the middle of this figure, it is the total biomass burning CO2 emission. We found that the largest amount actually was due to the burning of original cropland residue. And then is the forest. Here we use the same or similar improved method to quantify the biomass burning emission in Southeast Asia after collecting improved fire land cover background biomass density data. And our study showed a good agreement with the FAD for a while. And this result has been published in CRC prices. Next part, I want to talk about something about greenhouse gases monitoring from space, that is by satellite or remote sensing technology. The global carbon cycle here is the carbon cycles from 2010 to 2019 with average amount. The largest emitter of greenhouse gases and carbon cycles is the fossil fuel emission with 9.5 gigaton per year. And another large emission sources is the land use change with yellow arrow. And the two things are land uptake and ocean uptake. We know that the carbon sensing satellite system in the space nowadays accounts are as below. So the number of satellites monitoring the world's greenhouse gases could triple by 2013, and scientists are trying to work to make the probe data on carbon dioxide and methane as accurate as those collected by observations on Earth. So, nor the orbiting carbon observatory data sets and satellites, including GOSAT in Japan, OCO2 in NASA JPL, and TANSAT of China, and OCO2, and GOSAT2 of Japan, and OCO3. And this 5 carbon sensing satellite system are now on services, which can provide enough data sets for us to quantify and to analyze the carbon emission, carbon concentration, and its related study and research. And all these satellites are launched with the goal of to achieve the Paris Agreement, which focuses on whether countries are upholding their commitments to reduce greenhouse gases emission, and whether countries are achieving their emission goals. So the satellite is a very efficient method to map the spatial distribution and patterns of greenhouse gases. And I have worked in GOSAT project for 3 years. So in this part, I want to introduce something about the greenhouse gas observing. The greenhouse gas observing satellite, short for GOSAT, is created by 3 parties of Ministry of Environment of Japan, by JAXA, Japan Aerospace Exploration Agency, and National Institute for Environmental Studies. It has been launched in 2009. It was called the first satellite that can measure the carbon dioxide and methane of the 2 greenhouse gases. And the GOSAT-2 is the successor of the GOSAT, and now on service right now. The greenhouse gases observing satellite Ibuki GOSAT is the first satellite that measure the concentrations of carbon dioxide and methane, and the 2 major greenhouse gases from space by using its spectrum, absorptive spectrum. And the observation instrument on board the satellite is the thermal and near thermal sensor for carbon observation. We call it TANSO. And TANSO actually is composed by 2 units, FTS and CAI. FTS is used to retrieve the carbon dioxide and methane, and CAI is used to calculate the aerosol cloud in the sky. There are 2 tables showing the specification of FTS and CAI, and also the ground-based FTS, we call it TCCON site for GOSAT data validation worldwide, which has been managed by the Caltech in JPL. Here's the overview of GOSAT. The sensor here of GOSAT was developed by JAXA and Mitsubishi Heavy Industry Company. And L1A product of the observation data sets are managed or controlled by the JAXA. And from L1B to L2, L3, and L4A, L4B are processed by NIES NIS, National Institute for Environmental Studies. And actually, most of us are very curious or are very care about the dataset usage, especially in ecosystem processes and large source emission quantification. Here's the product of FTS L2, L3, and L4A. L2 products was generated by using 0.5 degree datasets, and L3 level dataset is 2.5 degree, which has been interpolated from the L2. And L4A flux data was generated by using the biosphere model. L4B is animated results. And before the data can be used, we are required to calibrate and validate the OCO and GOSAT datasets to test whether it can be applicable or whether it can be reliable. We selected the calibration validation study in Caltech, California Institute of Technology, and the JPL site in Nevada. Our member include NIES, JAXA, and JPL, and we use the site observation and jet plane and the satellite overpass, 3 kinds of methods to test our agreement of the data set. This is our team member in the desert of the Nevada area. And we use the EM27 and TCON comparison at GOSAT observation and Alpha Ajax flight data sets. The 2 pictures below are our results of the aircraft data sets and EM27, which showed good agreement. Actually, we calibrated the data sets and submitted our results to the team of GOSAT and OCO2 group to make further improvements. After calibrating and validating the results, we used GOSAT FTS L2 CO2 column data to make a further analysis. We selected the XCO2 from 2009 to 2015 and used the corresponding annual burned area product. We select the full high percentage of annual burned area worldwide and make comparison with the XCO2 datasets to test whether this high concentration come from the fire. So the GOSAT XCO2 is the net change between carbon sink and carbon source, and forest fire and XCO2 change of Indonesia accounts for 50%. Therefore, their correlations our issues. So first of all, we use the detrained method to detrain the XCO2 regional and its trained. And this line shows the detrained results. And the temporal variation may caused by the vegetation, may caused by the fires, and also may caused by the precipitation and other climate factors. And we make correlation coefficient. We finally found that in southern part of Africa, the detrained XCO2 and the fire emission, and their correlation coefficient can reach up to 0.77. So we can simply say that in this part, the fire is the main driving factors. And this result actually is the first test of fire of satellites can capture the fire CO2 emissions. As we know, the GOSAT observing the GOSAT observations are the result of human and natural. The carbon dioxide concentration or the methane concentrations are caused by human and natural. So how to define or how to separate the human effects, the human contribution? We use the geochems, atmospheric chemical transport model to separate the contribution of humans and natural factors. Here's the result. We found that in Asia, in Chengdu, Chongqing, and there the value is very high. While in Pakistan, the Lahore, and in Bangladesh, the Dhaka area also recorded very high emissions. In North America, for example, in New York, Pittsburgh, Chicago, and due to the urban area and the livestock and also the paddy field, their emissions are very high. And the same problem can also be found in San Francisco and Los Angeles. So the human methane emission can be derived from GOSAT observation. And this result was published in Japan NHK World and Asahi Shimbun. And next, we are trying to analyze the controlling factor for GOSAT XCO2. That means which factor can determine the change of and dynamics of XCO2. We collected the XCO2 concentration data and the human emissions by ODIAC and also the GFED for fire emission process and make spatial and temporal variation of each pixel by pixel. During the growing season of this 7 years, we found that after the vegetation is the dominant dynamic factors, driving factors of the regional XCO2 in China. Well, for spring, summer, and autumn, for different pixels, we have the main factors. For example, in spring, the human factors in northeast China and the fires in Yunnan province in southwest of China are the main factors. So in this study, we successfully achieved the driver of XCO2 dynamic into pixels, right? Another part is the mercury emissions in China, which has been quantified by our group member, including the energy, paddy field, livestock, wastewater, municipal solid waste, biomass burning, vegetation, and wetland. It includes 8 major sources to quantify the methane emissions with 1 kilometer degree. This is very valuable input data. Then we analyzed the temporal variation from January to December. We can find that the vegetation, wetland, paddy field, and livestock which show dynamics within the year, especially in the summer time. And after quantifying each of the main methane emissions from the 8 major sources sector of the annual value of each month in January and July for different provinces, we found that Inner Mongolia has the largest emission of mercury emission due to its land area. And number 2 is Shanxi province due to its energy use. And number 3 is in Sichuan province because of the wetland, the paddy field, and also the livestock. For different provinces, we have the different driving factors. And this is the recent work we did it currently. And last part, we want to talk about the power plant CO2 emission retrieved by satellite data. That means the CO2 emission for main large point sources retrieved by satellite observation. You know, the OCO2 data set is a reliable data set for carbon dioxide concentration measurements. And we use the Gauss plume model to retrieve the carbon dioxide, carbon emissions in the power plant area by using this model. After collecting all these required data sets, the CO2 emission of power plants retrieved from OCO satellite was achieved. First of all, we should select the appropriate or reliable coal power plants in China. And after co-located with the data sets, two power plants were as targeted in Shanghai, Waigaoqiao, and Henan Province, Qinbei power plants. And this is the two pictures below are our results, Waigaoqiao power plant and the Qinbei power plants. After comparing with other data sets, for example, CRMA, CPED, Carbon Brief, and other bottom-up methods, our results are reliable, showed good agreement with it. So this is the first time that by our member to achieve the carbon emission of large point sources using satellite data sets. And today I was very happy to share my study and my thinking and ideas with you from the perspective fire and biomass burning emission. We see that this part plays an important role in the global carbon-bodied and regional air quality. And the integration of the bottom-up method and top-down method is an efficient way to quantify the emission process more accurately. And besides, long-term time series of multiple satellite data, including GOSAT, OCO, TimeSat, on carbon dioxide and methane will be extensively employed in the integrated research on global warming and climate change in future. Finally, I want to thank everyone for your patience and your encouragement. Thank you very much.
Thank you, Professor, for your nice presentation.
Thank you, Professor Shi. And any questions from our trainees?